Good morning, I'm Daniela Novembre, and this presentation deals with the use of diatomite as natural precursor for the synthesis of KAlSiO4-O1. I conducted my studies at the University of Chieti, and for years I have been involved in developing green synthesis protocols of useful minerals, in particular zeolites and feldspathoids, which see the use of geomaterials instead of the expensive chemical reagents commonly used by industry. In practice, procedures that, on the one hand, reduce the cost of the synthesis and, on the other, enhance the georesources. The first aim of this work is to develop a new experimental protocol for the synthesis of KAlSiO4-O1. And a novel starting material is here used as the silica source, a naturally derived amorphous silica, a diatomitic rock coming from Crotone in southern Italy. This natural, inexpensive and abundant geologic resource has recently been used in other successful synthesis processes, particularly for the preparation of zeolitic minerals. I refer to papers by Boccadir et al. 2002, Sanwese et al. 2003, 2004, and Novembre et al. 2004. A natural, cost-effective starting material makes this route especially attractive when expanded to an industrial scale, as long as the material properties of the synthesized mineral remain satisfactory. The synthetic phase KAlSiO4-O1 represents one of the polymorphs of the mineral calcite, and for years it has been considered a material of technological interest. For example, high thermal expansion ceramics have been prepared from KAlSiO4-O1 for bonding on copper or silver. The material is of considerable importance in the context of high-temperature technologies, as it has been used in blast furnace linings, magnetohydrodynamic generators, and hazardous waste incinerator clinkers. KAlSiO4-O1 was first synthesized by Cook et al., who refined its structure with orthorhombic symmetry. Later, Kremenovich resolved the structure of single crystal of KAlSiO4-O1 in the monoclinic system. Cook et al. In 1977 investigated the transformation of KAlSiO4-O1 into the polymorph KAlSiO4-O2 at temperatures higher than 1450 degrees Celsius. The mineral has been synthesized in the past in a temperature range between 950 degrees Celsius and 1300 degrees Celsius by the solid-state method or by the flux technique. But in all of these previous studies, the authors chose to use commercial reagents such as silicon oxides, amorphous silica gel, potassium carbonate, zeolite LTA, and others. The starting material is a diatomite. It has a triple-aqueous siliceous rock called Tripoli rock, cropping out in the Crotone basin in southern Italy. Tripoli rocks are mainly opaline in composition and are originated by the accumulation of skeletal remnants of radiolars, diatoms, and sponges that fix silica dissolved at very low levels in natural waters. In particular, the Tripoli coming from Crotone represent an important economic resource, being concerned with a number of industrial uses. In general, Tripoli are used in a lot of technological areas. Most of them are based on the physical and chemical properties of these rocks. They are fine-sized, they are mesoporous and highly reactive. In general, opaline deposits are common in the Mediterranean area. This Tripoli is made of amorphous opaline silica, as it is visible from the diffractometric analysis. Is made of quartz, montmorillonite, chlorite, kaolinite, potassium micas, but Tripoli, coming from Crotone, also contains minor amounts of carbonates, about 4.8%, determined by calcimetric analysis. Macroscopically, this rock occurs as porous and friable, made of millimetric white and gray layers, and under the electron microscope, it shows a good preservation of opaline rests of diatoms. The siliceous solution was prepared according to the method proposed by NOVEMBRE et al. 2004. Tripoli material was treated with nitric acid in order to dissolve the carbonate fraction as well as other impurities such as nitrate compounds. The diatomitic sample was added to potassium hydroxide. This solution was accurately mixed and heated in an oven at 80 degrees Celsius for a day. After filtration, the remnant solid and insoluble fraction, which consisted of clay minerals and quartz, was separated from the silicate solution. After the insoluble solid fraction was separated, the K solution was filtered. The aluminous solution was prepared by mixing aluminum hydroxide with potassium hydroxide. Then the two obtained solutions were mixed together and the resulting molar composition of the final solution is here reported. After the chemical treatments, the Tripoli rock was determined to be composed of 32% amorphous silica, 63.27 weight% of clay minerals and quartz, and 3.83 weight% carbonates. The mixture was heated inside the autoclaves at 150 degrees Celsius and ambient pressure for a duration of 1 hour. Characterization by diffractometric analysis showed the resulting material to be amorphous, as it is visible from the figure. The gel precursor was then calcined at 1000 degrees Celsius and sampled at scheduled interval times. The crystallization of the synthetic KAlSiO4-O1 phase is evident within the time interval 2–5 hours. After this time, the presence of KAlSiO4-O1 is associated to that of leucite in the time interval 6–100 hours. It has the experimental run ends with the final overlapping of the two phases. A possible mechanism is that KAlSiO4-O1 would crystallize at first, then react with excess of silica, finally forming leucite. Actually, replacement of KAlSiO4-O1 by leucite with the time is consistent with the findings by Zheng et al. 2007. These authors, in fact, have found calcilite as the common metastable phase during the leucite crystallization process, when calcinating at temperatures ranging from 750 to 900 degrees Celsius. Here we present the observed and calculated profiles and different plots for KAlSiO4-O1, lucite and corundum-NIST 676A for the samples at 2, 4, 5, 6, 40 and 100 hours. In this table, the cell parameters for KAlSiO4-O1 refined with the monoclinic symmetry and of lucite refined with the tetragonal symmetry are reported together with the results of the QPA analysis. Cell parameters for both KAlSiO4-O1 and lucite remain constant within error as a function of the experimental runtimes. On the right, there's the volume of weight fractional change in the participating phases as a function of time. The most notable changes occur over the first 2 hours of the synthesis, as nearly 75% of the amorphous phase is transformed directly into KAlSiO4-O1. From 2 to 5 hours, this transformation appears to slow down, during which the maximum KAlSiO4-O1 fraction of 92.55% is reached before any lucite is detected. After 5 hours, the KAlSiO4-O1 phase is continually replaced by lucite, even though about 6–7% of the sample remains amorphous. At 100 hours, the sample is dominated by the presence of lucite. This is an image of a typical image of KAlSiO4-O1 crystal from sample at 5 hours, showing an average maximum length of crystals observed to be around 4 microns. The CL ratio is in good agreement with the results of Stabbings et al., who obtained a similar ratio for a calcite synthesized starting from oxides. We report the resulting stoichiometry of the as synthesized KAlSiO4-O1 together with the density value, which is in good agreement with the value obtained by Kremenovich et al. 2013. This is the infrared spectrum, which shows 8 partially resolved bands that can be identified in the high frequency portion of the spectrum. And these bands are due to the CO stretching vibration. 2 additional bands with lower shifts are evidenced, which are similar in frequency to those observed by Dmitrievich and Dondur, who interpreted them as being due to symmetric CO stretching modes. It is more likely that these lower frequency vibrations are due to LO stretching motions, as its bond strength is weaker than that of the tetrahedral ECO bond. Finally, this is the Cnmr spectrum that is characterized by a band located at 85.58 ppm, in good agreement with Stabbings et al. 1986 for a Q4 for calcite. In conclusion, we can say that this work described the synthesis of KAlSiO4-O1 using a natural, inexpensive and abundant geologic resource, combined with a simple but novel chemical process. A precursor prepared through a series of chemical treatments performed on a sample of diatomitic rock was hydrothermally treated at a temperature of 150 degrees Celsius and successively calcined at 1000 degrees Celsius. The presence of KAlSiO4-O1 as isolated phase is attested in the time interval 2–5 hours. In particular, the maximum abundance of KAlSiO4-O1 is observed at 5 hours, after which the phase is steadily replaced by leucite. The QPA analysis indicate a product at 5 hours constituted by 92.55% KAlSiO4-O1 and 7.45% amorphous component. The chemical, physical and spectroscopic characterization of the sample at 5 hours underscore the efficiency of the experimental procedure proposed here. Also, the results from infrared and NMR spectroscopic analysis are comparable with those reported in the literature for KAlSiO4-O1. Quantitative data suggests that transfer to an industrial production scale would be possible. Last but not last, the use of amorphous silica obtained by a georesource in place of commercial amorphous silica confers uniqueness and considerable low cost to the protocol, while enhancing a natural material through its use in a synthesis process. Thank you very much.